Welcome to the Explainer. Today, we're diving straight into the hidden, microscopic world of chemical bonding. We're going to see exactly how these invisible little atoms connect, how they organize themselves, and how they totally dictate the physical properties of, well, literally everything around us.
Take a look at these splashing ice cubes. It's easy to just see frozen water, right? But the macroscopic, real-world states of matter that we interact with every single day, whether that's a solid block of ice, a flowing liquid, or an invisible gas, they are entirely dictated by microscopic atomic behaviors. It's wild to think about, but the specific way these tiny, invisible atoms bond together perfectly explains all the physical properties we can actually see and feel.
So, here's our roadmap for this explainer. First, the basics of bonding. Second, ionic bonds and diagrams. Third, the properties of ionic compounds. Fourth, we'll hit covalent and metallic structures. And finally, number 5, we're going to cover some common traps to avoid so you don't lose any points on exam day. Let's get to it.
Section 1. The basics of bonding. Why do atoms bond in the first place?
Okay, so the absolute ultimate goal for basically any atom is achieving stability. And in the atomic world, stability means one very specific thing, having a perfectly full outer shell of electrons. And honestly, to get there, atoms can be kind of ruthless. They'll either completely lose their own electrons, steal them from somebody else, or, reluctantly compromise and just share. But every single type of bond we're going to talk about today is really just a different strategy to achieve that one goal, a full outer shell.
Moving right along to Section 2, ionic bonds and diagrams. This is the ultimate give and take relationship. Let's dive into this step by step using good old sodium chloride as our example. In step 1, sodium, which is a group 1 metal, has this one pesky outer electron that it desperately wants to get rid of to become stable. Meanwhile, over in step 2, chlorine, a group 7 nonmetal, is literally just one electron short of a full shell. So, it's a match made in heaven, right? Sodium just transfers its electrons straight to chlorine. And then step 3 shows the dramatic result of this. We don't have neutral atoms anymore. Now, we have a positively charged sodium ion, Na+, and a negatively charged chloride ion, Cl-. And the best part? Both of them now have those highly coveted full outer shells. Now, magnesium oxide follows that exact same logic, but with slightly higher stakes. Since magnesium is a group 2 metal, it actually needs to lose 2 outer electrons. Oxygen, being a group 6 nonmetal, needs to gain 2, so the transfer happens just like before, but notice the result here in step 3. Because 2 electrons were transferred this time, we end up creating ions with a much higher charge, a positive Mg2+ ion and a negative O2- ion. The underlying mechanism is completely identical, we're just dealing with a different quantity of electrons. Section 3. Properties of ionic compounds. We're talking giant lattices and electrostatic forces.
You see, when millions of these oppositely charged ions come together, they don't just pair up and call it a day. No, they build a massive 3-dimensional structure called a giant lattice. And the real secret behind these structures is something called strong electrostatic forces. Basically, these are the incredible forces of attraction between those positive and negative ions, and they are acting in literally all directions throughout that entire giant lattice. Now, because these electrostatic forces are so incredibly strong, it requires a massive amount of heat energy to break them apart. And that is the direct reason why ionic compounds have such notoriously high melting and boiling points. For example, magnesium oxide, with its 2+ and 2- charges, actually has an even higher melting point than sodium chloride, simply because those electrostatic forces are even stronger.
And this brings us to a brilliant illustration of a crucial contrast in electrical conductivity. Think about it. If you test a solid ionic compound, it will not conduct electricity. Why not? Well, because the ions are locked tightly into fixed positions within that giant lattice. They can't go anywhere. But if you take that same compound and melt it into a molten state or dissolve it in water to make an aqueous solution, boom, the lattice breaks apart. The ions are now free to move around. Mobility is absolutely the key here. Because the charged ions can physically move, they can actually carry an electrical charge.
All right, Section 4. Covalent and metallic structures. Time for sharing electrons in delocalized Cs.
So covalent bonding is a whole different ballgame. This happens between non-metal atoms. Instead of stealing or transferring electrons like we saw before, they share a pair of them. The bond itself is basically the strong electrostatic attraction between that shared pair of negatively charged electrons and the positively charged nuclei of both atoms. But here is where you really need to pay attention. Structure matters hugely here. Simple molecular substances like water or methane have strong bonds within the actual molecule, but they only have very weak intermolecular forces between the individual molecules. So when you melt them, you're only breaking those weak forces between the molecules, which means they have really low melting points. Giant covalent structures, on the other hand, are a vast, continuous network of strong covalent bonds, and those require massive, massive amounts of energy to break apart. Now, what's truly fascinating about this slide is seeing how the exact same element, carbon, can behave so incredibly differently based entirely on its internal structure. I mean, look at diamond. It's a giant covalent structure where every single carbon atom is tightly bound. That makes it extremely hard, it gives it a super high melting point, but it's a terrible conductor of electricity. Graphite is also a giant structure with a high melting point, but its layers can actually slide right over each other. That makes it soft. Plus, it has these delocalized electrons, which makes it a surprisingly good conductor. And then, look at C60 fullerene. Even though it's made purely of carbon, just like the others, it's a simple molecular structure, so it has a low melting point and it's soft, which is a complete 180 from diamond. Let's also take a quick look at metallic bonding. Metals form this giant lattice of positive ions that are literally surrounded by what we call a sea of delocalized electrons. And these electrons, they are totally free to roam throughout the entire structure. Honestly, this continuous free-flowing sea of electrons explains basically everything you need to know about a metal's properties. Because the layers of positive ions can easily slide over one another without shattering the overall structure, metals are incredibly malleable. You can bend them and shape them. And because those delocalized electrons in the sea are completely free to move around, metals are highly conductive to electricity. All right, we've made it to Section 5, Common Traps to Avoid. Let's open up the exam rulebook.
So the absolutely crucial point here is knowing the exact difference between these two very similar sounding terms. Ammonia, NH3, is a simple covalent molecule. It has zero overall charge, it's just happily sharing electrons. Ammonium, on the other hand, NH4+, is a positively charged polyatomic ion. Mixing these two up is such a common pitfall, so let's lock this distinction into your memory right now so you never lose points on it.
Next up, you really have to watch your suffixes. An "ide" ending almost always means a simple ion straight from the periodic table, like sulfide S2- or nitride N3-. But an "ate" ending, that means you're dealing with a complex ion that contains oxygen, like sulfate SO42- or nitrate NO3-. Oh, and here is a fantastic golden rule to help you quickly identify bonding types on the fly. If a compound contains a metal, it is almost certainly ionic. Keep that rule in your back pocket to anchor your thinking. Finally, we need to talk about some serious terminology pitfalls. You absolutely want to avoid using the word molecules or the phrase intermolecular forces whenever you're discussing ionic compounds. Remember what we said earlier? They form giant lattices, not molecules. And here is perhaps the biggest trap of them all. When you are explaining why molten ionic compounds conduct electricity, do not say it's because electrons are free to move. It is because the ions are free to move. Examiners are super strict about this. Precision in your terminology is exactly what proves you truly understand these core concepts. To wrap up the explainer today, I want to leave you with this final, kind of provocative question. We touched on it earlier, but I want you to really think through the mechanics here. If both substances are made entirely of carbon atoms, why exactly does C60 fullerene melt so much easier than diamond? Think about the fundamental difference between those giant networks of strong covalent bonds and the weak intermolecular forces sitting between simple molecules. Keep that concept in mind, chew on it a bit, and you will have officially mastered one of the core secrets of chemical bonding. Thanks for exploring